Okay, let's continue on with running water and look at stream channel patterns, which include straight channels, meandering channels, and braided channels. Meandering channels have many bends, and if we look at the straight segment, we find that the maximum water velocity is mid-channel near the surface, as shown in this little figure on top. And again, this is simply due to the mid-channels being the part of the overall stream that experiences the least amount of frictional resistance with the sides of the channel. Now, when entering a bend within the meander, the maximum water velocity shifts to the outer bend, and the net result is that there's erosion of the channel wall to create what's called a cut bank. At the same time, water velocity decreases in the inner bend, causing deposition of a point bar. So that over time, the meandering channel will actually shift from one place to another because of the deposition on the inner bend, erosion on the outer bend, to the point that if you look at that photograph in the upper right-hand corner, that house is precariously close to the cut bank that's undercutting the foundation. I hope he moved. If not, he's probably sleeping. He's going to fall in. Anyway. Look in the well, here, let's look at this photograph here. Notice that within this meandering channel, the inner bends always have net sedimentation and formation of the point bar, whereas the outer bends are the sites of net erosion where the cut banks are located. Meandering channels form typically where the gradients are low and the load is generally fine grained, typically silts and clays. It's a very common pattern, actually. Meandering channels end up forming what are called oxbow lakes. For example, in this figure, and that one bend to the left, this is going to be the location of the future oxbow lake. And notice that over time, as we get erosion of the outer banks, this causes the two segments of the bend to approach one another, creating what's called a neck. And eventually, the outer banks will meet, diverting the overall water flow. Over time, the abandoned meander will eventually become isolated from the main stream by plugs of silts or clays, creating what's called an oxbow lake, or basically an abandoned meander channel. And here's a photograph of an oxbow lake. These things are typically fun to watch when looking out the airplane flying at 33,000 feet, flying over places like Arkansas and Missouri and so on. There's not a whole lot else to do on planes, so next time the skies are clear and you're flying, look for oxbow lakes. That's kind of a fun thing to do, at least for me. Anyway. Now sometimes, particularly in areas undergoing uplift, incised meanders can form within a steep, narrow valley. And the formation of incised meanders typically results when the land is uplifted, as for example occurred with the Colorado Plateau. And as a result, the stream actively downcuts in order to achieve its new base level. Braided channels are patterns that typically or repeatedly divide and reunite. And channels are separated by these bars or islands, typically where the coarsest sediments are deposited. So notice that the channels, they divide and then they come together again, leaving these bars in between. And quite often the positions of these bars will shift over time as they erode and become redeposited someplace else. These braided patterns develop in streams with highly variable discharge and large loads of sediment to transport. So typically you'll find these in areas of rugged terrain with lots of hills, mountainous terrain, things of that nature, where great deal of erosion is occurring and a lot of sediments being introduced into the stream. We can even define two types of stream valleys, narrow valleys versus wide valleys. Narrow valleys are typically V-shaped in cross-section and are indicative of a stream that's actively down-cutting towards its base level, and features often include rapids and waterfalls, whereas wide valleys are characteristic of streams that are very near base level, where downward erosion is less dominant and the stream energy is directed from side to side, forming a wide floodplain. So here we start out with a steep, narrow V-shaped valley where a stream is actively down-cutting towards its base level. And over time, here is a picture of a V-shaped valley. This is the Yellowstone River actively down-cutting. And we can see it also includes waterfalls and rapids. This river is actually down-cutting through rhyolite, volcanic deposits. However, as the stream approaches base level, the downward erosion becomes less prominent and the energy is directed side to side. And over time, and eventually when the stream reaches its base level, side to side erosion creates a wide floodplain with many meanders, oxbow lakes, things of that nature. The main features of a stream valley include the stream channel, the adjacent floodplain. We may also find terraces, which mark former floodplains, as well as natural levees, which, as we saw before, are built or constructed along the edges of the channel during flooding episodes. Now, stream terraces form when streams downcut through previously deposited stream sediments known as alluvium. And a downcutting stream will carve a new lower floodplain, leaving behind the older floodplain as a terrace, such that with significant downcutting, multiple terraces can result on both sides of the stream valley. Typically, stream terraces are cut during times of global sea level fall, as for example occurred during the last ice age, where ultimate base level was quite a bit lowered. And so when you drive when you're crossing, like for example, the Mississippi River, you'll travel across several terraces on both sides. And those terraces were largely formed during the last ice age when global sea level was significantly lower. Now, adjacent streams are generally separated by topographic rises or ridges that are called divides. And a drainage basin, by definition, consists of all the divides that separate one stream and its tributaries from a neighboring stream. So in other words, precipitation that falls within the drainage basin to the left all that runoff will collect into that major stream running through the central valley. On the other hand, precipitation falling into the drainage basin to the right will collect within different streams. And those drainage basins, in turn, are separated by these drainage divides. Now, the size of drainage basins can range anywhere from small areas, such as ravines, to very large regions covering several states. For example, in the upper right-hand corner of the map of the U.S., notice that the Mississippi River drainage basin covers almost 1/2 of the entire country. However, the Mississippi basin can be further subdivided into smaller second-order drainage basins like the Missouri, the Arkansas, the Ohio, and the Tennessee basins. And if we just focus to the Missouri drainage basin, those drainage basins can be even further subdivided into smaller basins like the Yellowstone River drainage basin shown on the left. So basically what's happening here is that the Yellowstone River is flowing northward and entering and feeding into the Missouri River, and the Missouri River, which comprises is part of the Missouri drainage basin, will eventually flow into the Mississippi River and become part of the Mississippi River drainage basin. And from there, the Mississippi River will flow into the Gulf of Mexico and deposit the Mississippi Delta. Poor Custer. George Armstrong Custer had bad luck at the Bighorn River back in 1876, but that's another story. Here we have a slide of the Harris County watersheds, basically drainage basins within our area. Me, for example, I live within the Brays Bayou drainage basin, which I'm sure you're all excited to hear. Now, there are different types of drainage patterns. We have, for example, dendritic drainage, rectangular drainage, radial drainage, trellis drainage. Dendritic drainage patterns are like branches of a tree that characterize most streams and rivers. These dendritic patterns typically develop in highly uniform bedrock in topography that's, for the most part, flat to gently undulating. The Mississippi River, the Red River are good examples of this type of pattern. Radial drainage occurs where streams flow away in all directions from a central high point, such as a volcano or maybe a dome. We would expect this type of drainage pattern to occur, for example, along the Cascades of a volcanic range of Oregon and Washington. Rectangular drainage is characterized by straight segments of streams taking on perpendicular bends, and basically here the streams are just simply following joints within the bedrock. In this example, we have two sets of joints that intersect at 90 degrees, so the 90-degree bends is simply the streams following the overall joints, the paths of least resistance, in other words. Trellis drainage has tributaries trending in parallel valleys of steeply folded terrain in areas of alternating weak and resistant bedrock. And this type of pattern is typically found in, for example, the Appalachian Mountains, particularly in places like Pennsylvania. This is analogous to the trellis on the edges of your roofs that collect runoff from the roof into the trellis and go down the drain pipe. Notice that the trellis drainage patterns ultimately end up in the major stream that cuts across the overall topography. Now, a stream can lengthen its course two ways. First of all, the stream can build a delta at its mouth, and secondly, as a result of headward erosion. Headward erosion may result in stream piracy, which is simply the diversion of the drainage of one stream into another stream. In this example, we start out with two streams, A and B, which occur in different drainage basins. But if we focus on the tributary of stream A, notice that tributary is gradually eroding back via headward erosion. And what's going to eventually happen is that tributary is going to erode far enough back to eventually capture the water in stream B, and as a result, the stream B is diverted into stream A as a result of this headward erosion, creating what's called a water gap. Further down in stream B, we're left with a dry former channel that's largely been abandoned. A water gap is a notch where a river cuts through a ridge that lies in its path. And water gaps form two different ways. In one case, we can have what's called an antecedent stream, where the stream existed before the ridge was formed. And as the ridge grows, the stream simply downcuts and keeps pace with the rising topography. Another case is that of a superposed stream, where the stream is let down upon a pre-existing structure. Here, for an example, we see the development of a superposed stream. Initially, notice that within the deeper part of the block diagram, we have folded structures, essentially an anticline. But then we have an angular unconformity, which is overlain by horizontally layered sedimentary rocks. So we start out where the river establishes its course on the relatively uniform strata, at this point covering the structural feature below. But over time, as the stream continues to downcut, it'll eventually encounter the underlying folded structure. And when it does so, it'll cut through the resistant rock and carve these gaps through the ridges. And a good example of this is the Bighorn Basin, where the superposed stream has created a water gap through the Wyoming sheet mountain. Does anybody know what a flood is? Yeah. Now, floods are the most common and destructive of all geologic hazards, and result when the stream is unable to accommodate the dramatic increase in discharge. Water at that point will then overflow the banks onto the floodplain, and floods result from naturally occurring and also human-induced factors. But this is a hydrograph, a plot of discharge versus time, and we see before the storm to the left, discharge is at average values. The stream is well within its bank. But then we get this sudden thunderstorm with lots of precipitation. And at that point, there's an abrupt increase in the discharge, and that's when we get the flooding event. And the increase in discharge peaks within a nearby stream, peaks following the storm. But over a period of days, the stream will then return to normal well within its banks. The upper figure shows a hydrograph, and notice there's a lag time between the rainfall and the actual peak of flooding within a rural area. But if we compare the upper diagram to the one for an urban area, notice that the lag time becomes much shorter in urban areas. And this is because of several factors. First of all, in urban areas, there's less exposure of soil and vegetation for infiltration to occur. Instead, runoff is quickly channeled into a drainage system, and the large discharge occurs in nearby streams over a very short period. There are several types of floods. Probably the most common is what's known as a regional flood, regional floods are typically seasonal, resulting from rapid melting of snow and or heavy spring rains, which temporarily overwhelm streams and rivers. Regional floods can affect large regions covering millions of acres over several states, and often result in significant economic loss and damage. Here, for an example, we have a satellite view. The upper frame is the Mississippi River back in, July 1988, and the lower frame shows the major flooding of the Mississippi back in 1993. Flash floods occur with little or no warning, resulting in a very rapid rise in water level and velocity over the time period of minutes to hours. Mountainous terrain is especially susceptible to flash floods, where the steep slopes funnel runoff into narrow canyons, and these small drainage basins tend to be overwhelmed quickly. As for an example, the flash flood that occurred in the Big Thompson River in Colorado back in 1976, which claimed about 139 lives over a brief 4-hour period. Ice jam floods result when frozen river occur when frozen rivers are susceptible to these ice jam floods. What happens is that rising stream level, particularly in the spring, will start to break up the ice. The ice flow will then accumulate on channel obstructions and create temporary ice dams, and as a result, water trapped upstream will overflow the channel banks. This often occurs in places like South Dakota, for example, and Minnesota, places like that. And then we get those darn failures, those dam failure floods, which occur obviously when the dam or artificial levee breaks. A large flood may cause the dam or levee, for example, to fail, such that the water behind the structure is then released as a flash flood, as, for example, occurred in the aftermath of the dam failure in Johnstown, Pennsylvania, back in 1889. There are various attempts at flood control. There are engineering efforts, and there are also non-structural approaches through sound flood management. The engineering efforts include the construction of artificial levees, flood control dams, or channelization, which involves widening, deepening, or straightening of the channel. As, for example, they've done with Bray's Bayou near the medical center. There are also non-structural approaches through sound floodplain management, and they include flood frequency curves, floodplain maps, and zoning. Now, engineering efforts at flood control, for example, can be the construction of these bypasses, construction of a bypass, the construction of artificial levees along the banks of the stream, dams which impound water behind the structure, and can be these dams can undergo selective release of the water downstream to try to prevent downstream flooding. Unfortunately, it doesn't help the people upstream of the dam. And there are no examples of that around here, like the, what's an example? Lake Conroe, Lake Livingston. Now, a channelization involves the straightening of a channel which supposedly moves water through the area faster to accommodate increased discharge. Unfortunately, straightening of the channel also creates problems. For example, the decreased habitats, a reduction in streamside vegetation. Also, as you increase the velocity of the water through straightening of the channel, this also increases erosion because the water is flowing faster, and ultimately results in downstream flooding at the next bend. But here in the lower pair of photographs, we see before and after pictures of channelizations, basically channel straightening. Another method is the construction of these flood frequency curves, which are useful to determining such things as construction sites, overall zoning, flood insurance, and development of flood control systems. These flood frequency curves requires a record of annual peak discharges over many, many years, possibly extending back over a century. And basically, these construction of a flood frequency curve utilizes this simple equation, R equals n plus 1 divided by m. R is what's known as the recurrence interval. N is the number of years on record, and the magnitude rank is basically what's shown in the upper right-hand corner of this table. What you do is, for a particular river, rank the years in order of discharge, beginning with the year of maximum discharge. In this case, 1997, followed by the year with the next highest discharge, and on down the list. And here we just assign magnitude rankings. A number one corresponds to the year of the highest overall discharge. And n is just a number of years in record, and then from there you calculate the reoccurrence interval. So you see the reoccurrence interval is the horizontal scale, and the peak discharge is the vertical scale. So, for example, if we take this upper frequency curve, the 100-year flood, for example, as red at the bottom of the figure, we just project this up to the red curve. This corresponds to a peak discharge back in 1997 of about, 88,000 cubic feet per second. That's how these things work. Other things we can do is the construction of maps using geographic information systems. Basically, this is a way of constructing a map of an area of elevation, and then through use of this extensive platform, you can fill up the lower elevations modeled by adding water to it, and then just see basically what areas flood. As, for example, this Hurricane Ike inundation map. And of course, there are also floodplain maps that are published by FEMA, Harris County, and private consulting firms, which are readily accessible on the internet. Something you may want to do if you want to buy a new home check out to see whether or not that area is prone to flooding. Yeah, start a business or maybe rent boats. If you want to rent a boat, maybe pick a place that's going to flood 3 or 4 times a year. I don't know. Whatever. Anyway, any questions? And this is our favorite slide again. So